opening day of talks, the IFML joint Simon's mini workshop here. Thanks to Kalani for helping organize everything, and to Sanjay and Chuchi, Sandy for letting us get together. And people ask me what is IFML. So briefly, I think everyone here knows what it is, but in case you weren't at our annual report meeting, we just some very brief stats. Last year, we had counting all the publications from all the work that IFML supported. We had 111 publications. We had 2 best papers in Europe's. We counted up 125 seminars that were actually given as part of some IFML sponsored events. Supported 37 students, 7 postdocs, and we had a variety of workshops and social events and trips. So we like to make it to Simon's every year if we can. And yeah, so Sanjay, do you want to say something about the program today?
Yeah, so today we are having a workshop jointly between the IFML and the resident program this semester, which is the data-driven decision process. So this morning we'll see 3 talks from sort of learning/optimization theory, and in the afternoon we'll have 3 talks from the data-driven decision process, broadly OR, econ, DCS, stochastic networks type communities. So thank you again to Kilani for all the help in organizing this. And so this is a workshop that Shuchi, Adam, and me co-organized. So we just get started. The first speaker today is Surbhi Goel. She's at Microsoft Research NYC and going to UPenn. Surbhi.
Thank you so much for inviting me to give this talk. Today I'm going to talk about transformer architectures and kind of the representation properties. I will define everything so that everybody's on the same page. So feel free to ask any questions and feel free to stop me in the middle. Okay, this is based on joint work with some awesome collaborators. Some of them are at Microsoft Research and some who passed through as interns during my time at Microsoft Research. And here is one. I always put some DALI to prompt these days on what transformers are doing these days. So this is a prompt on, I just put an Institute for Foundations of Machine Learning, and it produced some cool artsy looking picture for this. So I thought this people would find fascinating.
Didn't give the logo though.
I mean, you haven't given enough hats to people yet.
No, Raghu said that our logo looks better than that. So. No,
I mean, this is very artsy.
No, that's not what I heard. Yeah.
Okay, so let me start. So we all know that in the last 5 or so years, attention-based architecture, especially transformers, have become really popular. And they've seen applications starting from natural language to like symbolic mathematics, vision, reinforcement learning, even in biology, automated programming, and this list goes on and on. And people find new ways to use these architectures. So one crucial thing about these architectures is that they remove these previous notions of things that we used to use, which were convolutions and recurrence. And they added this new notion of self-attention. I'll describe what self-attention is. So the question that we wanted to understand was that these architectures that we used before convolutions and recurrence kind of encoded some prior beliefs that we had about the data that we were processing. So for example, in CNNs, we wanted to model some sort of translational invariance, and with the RNNs or any recurrent architecture, we were trying to model recurrent structure in the data in a sequence-to-sequence modeling task. So transformers here kind of removed these things. So it wasn't clear what kind of inductive bias these transformers were adding into our architecture. So this is the overriding question of this talk. What kind of functions do these transformers represent? So if we look back at the intuitions and the guiding principles that people came up with while they were designing these architectures. So from the original paper, this is a quote that is from the original paper, that these architectures were intended to capture these shorter path lengths between long-range dependencies. So they wanted to capture these long-range dependencies in a fashion that all of them were simultaneously captured instead of in recurrent when you do one at a time. So they were hoping that they can find shorter path lengths between these longer dependencies. Some other work from the vision space suggested that this has some like a more relaxed or weaker or softer inductive bias compared to CNNs, because CNNs you're fixing the window that you're looking at, but here this window is kind of open-ended. You can the architecture can learn what window to focus on. And then there's a lot of work trying to understand what kind of functions these architectures are learning. For example, there's this whole area of Bertology, which kind of tries to decipher from attention heads like what kind of structures they're learning. So for example, here, these are like trained BERT models, and these are heads that you can interpret to say that they're doing some natural language task. And this is another one from an RL application of these transformers, and you can see there's some kind of structure of how they're looking back. So these are like attention maps are kind of like what part of the text you're looking at in the history. So something that's observed commonly is that these attention weights, which I'll describe what they are exactly, tend to be of these two modalities, that either they're very sparse, which you can see from here, even these red edges are sparse, or they are sort of uniform. So they look at everything together. So this kind of two modalities exist. And from a mathematical perspective, if you want to quantify such properties of these architectures, the standard way to look at this is like we can think of this as a function class F. So here, this is the function class of transformers. And then you can ask this question about the capacity of this function class. So how rich is this function class? How many functions are there in this class? And like how many samples do you need to learn this function class? Then you can ask a representation question that given the capacity is somewhat bounded, then what kind of interesting functions are there in this function class? And lastly, you can ask the hardest question here, that finally you're training these models with gradient-based optimization algorithms, and what kind of functions do they actually learn? Okay, so with that, I'm going to start today's talk. I'm going to start with the Transformers 101. So I'll describe exactly what this architecture is. Then I will talk about the representation power of a single component of this transformer architecture. And then I'll talk about the representation power of shallow transformers. And then I'll end with some questions that I'm still thinking about. Okay. So let's start with Transformers 101. So transformers are sequence-to-sequence models. So they take in input, which is t tokens of d dimension each. So you can think of a sentence as a t-length sentence, and then each of these words in this sentence can be thought of as a vector in some d-dimensional space. So here x1, x2, x6, and this you can think of some word embedding. So taking these words into some embedding space. And what you want to output is another sequence of tokens. So you want to process them somehow that you get a new embedding such that this embedding now has context of what was in the sentence. So because before you just started with some embedding which was independent of each words, and now you want the new embedding that somehow depends on what is in the sentence. So if you look at this particular word, you want this word's output to have some relation. And the way to do that is like you want to find some weights that this word assigns to every other word. So you can think of these as the weights, and you want to sum these weights up with the features of these words and get the new embedding. So this is what the attention network is trying to do. And these things you can think of as attention weights, because these are kind of weights that how much are you attending to another word in the context. Okay, so now the question is, how do you actually generate these weights? And so the transformer architecture does it in the following fashion. So first, it computes these pairwise scores. So between every word, so I'm just focusing on this word's embedding right now. So it computes a score function between this word and any other word in the context. So this will be score x1, x4, x2, x4, and so forth. And for every different word, you would have these pairwise scores. Okay, so once you have these scores, generally, so on the right, I'm just showing what the exact transformer architecture does, but you can have any kind of score function that you want for this generality. For the transformer, it's just a dot product of linear functions. And once you have these scores, these are unnormalized. So these are passed through a softmax to get these normalized score weights. And then the embedding is averaged with these weights. And this is the only place, note, that you're having a global interaction, because these are all pairwise interactions. So here the softmax kind of adjusts how much you should care about each word by normalizing these scores. Okay, so this is basically one self-attention head that you compute. And here on the right, if you see, these are all the parameters. That the ones in red are the ones that are learned. So it's learned end to end, and you train all the red parameters. Okay, so one thing, if you've noticed, this architecture has is that if I permute any of these coordinates and I permute the output, it doesn't really change. So it's not really accounting for the position of where everything lies by the structure that it has. So one thing that's commonly done is that there's a positional encoding that's added to each of these positions. And this kind of ensures that there's some positional information of how the context is created. Okay, any questions on this?
So that's just one head at the box, right?
Yeah, so you get, basically you can use these same parameters. So these are just fixed parameters you can generate for each of the different words, you'll get this embedding. So they'll create different, the score function will evaluate to different things for different words and you'll get the embedding. But this creates one layer of this. Let me show you. So this basically generates this, but in practice, what you do is you take multiple of these attention heads, then you concatenate them, you can add and normalize them, you get your output. Then you apply like a fully connected layer, which is the same one that's applied to each of them. So it's like shared across. So it doesn't add any dependencies between the tokens. And you can apply this many, many times. You can, if you want to do a supervised learning task, you can learn a linear classifier at the end and get a label or so forth, whatever you want to do with the sequence to sequence model. So this is the entire architecture that I'm going to focus on. There are many other things that happen. But this is what I'm going to focus on. Any questions?
I think this is just figure out which pairwise correlations are important. Or...
Yeah. So the softmax will kind of wait. So some pairwise correlations will be more larger than the other ones. So the softmax will kind of put more weight on them. And so you're going to take in your new embedding. So yeah, so here these weights will be larger. So in this, like say this weight is larger. So this feature corresponding to this will have more of an impact here. So this will kind of model what is relevant in the context. Yeah. Okay. So so here I showed you what self-attention was, and then I talked about what token that these implement token-wise feed-forward layers. This will be important later in the talk. So let me start with the main results of trying to understand what these single self-attention heads do. And the first question that we'll ask is, what is the capacity of this class of attention heads? And how many samples do you need to learn them? This is completely a statistical perspective, not a computational perspective. So the first result we have here is that if you use a notion of covering numbers as the capacity measure, then the number of samples that you need to guarantee uniform convergence is of the following form. So there's a polynomial dependence on norms. So these are the norms of the parameters that you bound. And there's a logarithmic dependence on the sequence length, which is the length of the number of tokens that you had. So the t here, and the error being epsilon square. So note that the sample complexity has this sparse L1 regression kind of complexity because there's a logarithmic dependence on the input sequence length. So this cannot represent functions that are very rich in the input sequence. And generally, you can handle like other kind of attention mechanisms and general choices of these functions that I mentioned before. So, yeah.
Just examples where you do weights.
Yeah, so let me just show you the next point. So here the one thing to note is that if you look at the architecture, you're sharing the same weights across. So the number of parameters here is actually only d squared. So the number of parameters does not depend on t, but you can show that if you don't bound the norms of these attention heads, then even if your dimension is 3, you require log t samples to guarantee uniform convergence. So you can shatter log t points. So this capacity of this class is larger than the number of parameters if I don't bound the norms of the parameters here.
How much bounding you doing experiments?
So actually for this, we need just t square, I think. So it's polynomial in t. I'm not sure this is tight, so I don't know if you can do better than this. So you can construct this log t shattering, and it's like some simple construction, some circular construction that you can get. So for every t, I can construct a log t points that can be shattered, but I don't know if that's tight. You can do better or not. Wait, let me go back from this because otherwise I'm not sure. So here, note that the embedding is all in d dimension.
Yeah.
And then you're computing scores, which you're taking a linear map on this d-dimensional output, and you're taking a linear map on another d-dimensional output and taking the dot product. So this is only a d cross d matrix, wk and wq. And then the weighting comes from the softmax. The softmax combines these t scores and then like scales them.
But the coefficients of the softmax, there are t coefficients.
Yeah, they're t coefficients.
So there are t parameters there.
I mean, the number of parameters that you're training are only.
Oh, you're not
D.
training the alphas there.
The alphas are computed based on the scores,
Oh, I
right?
see.
I'll pass the score through a softmax and then I'll get the alphas.
So why do I expect any dependence on t?
Yeah, so you might not expect any dependence on t, but if you don't bound the norms, that the lower bound that I showed you. Yeah, so if you don't bound the norms, you can actually show that because of this attention mechanism, it's not a linear function. It has like some non-linearity. You can actually shatter points that depend on t, even if your dimension is 3. So the number of parameters that you're using is only 9 here, but you can shatter more points.
Okay.
And the reason is because what happens is in this construction is that you have these attention weights. These attention weights you can design such that you can pick out each of the token based on different parameters. And so they're t tokens, so you can pick out these t different tokens for different inputs. And so that gives you power.
You need the position embedding.
Yes. Yeah, the Bayesian.
Oh, okay.
Yeah, so but note that I'm only using 3 dimensions, so I just use the position encoding in 2 dimensions and the value in 1 dimension. So I just need 3 dimensions to do.
But then one of the entries is growing t.
It's not growing with t. So because the position embedding I take is that on a unit circle, I just take points on the unit circle uniformly distributed on t. So yeah, I mean, if you talk about bit precision and all, yeah, you have some t dependence there. Okay, so now that we know that the capacity is bounded, does this actually represent interesting functions? So what you can show is that if you talk about Boolean functions, then this can approximate arbitrary sparse Boolean functions with norms scaling as a function of sparsity and log t. So I mean, the question is how you can map Boolean functions into this this feature space by mapping your bits into this this sequence token sequence. So a way to do this is that you can take your input, you can take an embedding for each bit. So bit 0 can be mapped to one embedding and bit 1 can be mapped to another embedding. And then you can add this positional encoding and this fixed position encoding, and that can map your Boolean function into this language of sequence to sequence models. And you can do this with trainable position embeddings and other ways without positional encoding also. So this might address Raghu's question. So if you don't have position encoding, you can still kind of map, if you have enough dimension, you can map any Boolean function into that language by assigning a token for each position, basically. So I can have a vocabulary that is log t sized, but then I can, if this position is bit 1, then that token appears in the text or not. So with embedding dimension, something that's a function of log t, you can get to represent all sparse Boolean functions in this setting. So even though the capacity is controlled, you can still represent interesting functions in this class. So the idea is that your self-attention can help you pick out the relevant tokens. So it can assign a lot of weight on the relevant tokens. And then the fully connected net can implement any arbitrary function on the selected tokens. Now the selected tokens are only S. So this function can have like norm as large as 2 to the O of S because there are that many functions that exist. Okay, so attention is promoting sparsity, but the fully connected net is doing the heavy lifting of actually computing the function. Another thing that you might have noticed that this function class can do is that it can focus uniform attention. So if it puts all the parameters as 0 by giving everything equal weight, it can do a uniform averaging also. So this is the other modality that this function class can compute. Okay, so together, taking these two together, so we said the capacity is of this form, and we can represent any sparse Boolean function with this norm bound. So combining this, you can get that these classes can learn sparse functions at statistically near optimal sample complexity, which is a function of the sparsity and polylogarithmic in T. And the interesting thing is the number of parameters that you need are only polylog. t for this. So you don't need t number of parameters to do that. So this we call like this has like the sparse variable bias, that each attention head is creating some sparse variable in the input. So you can think of these as small norm attention heads are like some computing some concise simple gates of your circuit with a good sample complexity. Any questions? Yeah.
No questions, sir. What exactly is T supposed to be analogous to on the sparse regression?
T is the length of the sequence.
Yeah, but in the sparse regression, what is it? Is it?
It's still the length. So think about the input dimension. And S is the sparsity. Okay, then let me explain why such a thing happens. And the reason we say is that highlight is that the softmax has this two nice properties. So it has these two phases. One is that it's really smooth as a function. So this property holds that there's an L1 L infinity smoothness, which means that if I perturb all the inputs to the softmax, the L1 norm, which is a distance between t things, only depends on the max of the change between any of the parameters. So this gives us this really smooth function, which allows us to capacity control, because now this L1 distance change can be bounded by only an L infinity change in the input. So this allows us to get this log t dependence. And the other thing that softmax has this exponential saturation, which means that if I put a lot of mass in one direction, then it really gets close in L1 distance to that direction. So if E1 is the indicator for the first coordinate, then if I put C times E1 in the softmax, then it goes exponentially fast to picking up that coordinate. So I need norms for token selector, I need norms only logarithmic in T to be able to actually select a token. So these two facts of softmax being very smooth and also acting as a selector helps do this task. Okay, then you can ask what happens when you actually try to train these in practice. So we try to train simple sparse Boolean gates. And this is a very simple function. You learn a three-way AND of t-bit input. So this is just what the label is just the x1. So we choose three indices randomly, and then the label is just the product of these indices. And this is what we found. So this is on the x-axis is the sequence length, and the y-axis is the number of samples that was needed by this transformer to learn. And note that this is on the log scale. So this kind of looks like linear in that log scale. So even for sequence length about 1,000, only about 100 sample, roughly 110 samples were needed to actually train this. So it can actually train in this low sample regime. And this statistical threshold is like consistent with log t. Even if you train the position embeddings. So if you train position embeddings, those are actually t cross d dimensional. Even then, it actually works. And you can see that the attention weights actually pick out the relevant coordinates. So they're actually learning which coordinates to look at.
What embeddings do you start with?
So we tried both trained of, so one thing you can do is just take two random orthogonal, somewhat orthogonal vectors. So that is one embedding you can fix, or you can even train the entire embedding matrix. So you can just have like two tokens, you can train these tokens. So both work.
What happens on parity?
Oh, so I don't have it in this talk, but parity also works. Though it doesn't work in the simple sample complexity, it doesn't work with very small sample complexity. Only in very small t it works. But if you do in online fashion, like your online gradient descent, it actually learns parity. And actually many architectures learn parity. They require n to the k steps to do it. Okay. So any questions on this part before I go to how to use this intuition to actually say what more like shallow transformers actually do? Yeah, so the main key, yeah.
I mean, it seems like some of the key things you talked about were just properties of softmax.
Yeah.
So like why, you know, if you've given this talk and just shown me like a bunch of MLPs and then like softmax and another set of MLPs and softmax, like I would have thought, oh, okay, the same thing happens, but it doesn't. So I mean, there's something else going on.
Yeah, so that's special, right? The fact that there is the same parameter that's shared on all scores, all functions. So there's only d parameters. Now, if I actually put a fully connected net with t parameters, then I would have a much richer complexities, and the softmax will not be able to smooth it out. So there's this like nice fact that there's this pairwise code that is being computed and is passed through a softmax that helps us get this result. Otherwise, yeah, if I put like more and more parameters, I can't guarantee anything. So the structure is very important for it. And even if instead of the pairwise,
Well, I could have more. I mean, I could have more parameters, but just bound norms of weight matrices. I mean, that would be. I could still control capacity that way.
You can still control capacity, but it's not clear that you would actually get that in the structure. So here, what happens is, okay, so if you see here, you get this property of the softmax. So now you need to cover this particular quantity, which is the distance that it moves. So here, the good part is because they are all shared, the same parameters are shared. I can only have to cover a matrix that's only d cross d dimensional. And it's subspace. So if all these parameters were different, then I would actually get covering something that has t different parameters. So that really helps in the capacity control. So otherwise you can actually express many rich functions if you allow for everything to be different. Yeah. Okay. Okay, let me, so I have to probably rush to the second part. So one thing I pointed out that these architectures also let go of recurrent structure, right? So there's no weight sharing across layers, and they only usually in practice are only a few layers deep, like maybe 10 or 12. So we thought about like how can they actually learn, and they seem to be doing really well on logical tasks. So they seem to be learning some recurrent dynamics. So we looked at this perspective of learning these sequence to sequence problems where you have an input of sequence tokens sigma 1 to sigma t, and the output is a sequence of states such that the state is basically generated from the previous state and the input token. So this is just a simple finite semi-automata that we look at, and we try to see that if transformers can learn this kind of function class, given that they have no recurrent structure at all. And so some examples of these are, you can think of these as, these are very simple ones, parity counter. So it can compute parity of given the sequence, the state can be the output of the parity bit. It can also do some memory operations, which is like it can learn what is the previous memory that it should, previous time the memory was set, and it should just output that. Some things more complicated from reinforcement learning, it can predict which state you are given an action sequence. So these models are pretty, structures are very general in language, code generation, reinforcement learning, and control. And so the question we ask is, can shallow transformers with no recurrent structure learn these recurrent dynamics? And what you can show is that transformers can represent these semi-automata with shortcut solutions. So they require only depth little o of t, much less than the recurrent depth that's needed. And so you get order log t depth for all. So for a certain class of semi-automata, you can get poly in the state size. And then for some special classes of automata, you can actually get even constant depth solutions. And these have analogies to circuit complexity for different circuits. So these constructions are kind of inspired by circuit complexity constructions, but they fit really well for the transformer architecture. And I'll just quickly show you why. So these constructions require basically boils down to computing two kinds of automata. So one is modular counting, which is just counting modulo some number. And the second is a memory lookup, which is like looking back at the sequence and finding the closest position where you set your value. And these two, and then combining these two together. And the good part about these two functions is that these fit very much into the attention framework that I described before. For example, the modular counting can just be done by doing a uniform attention on everything and taking a modulo p. So this is just taking the sum mod p. And the memory lookup can be done using the sparse attention because it only has to find which closest position it has to look at. So this is a sparse attention head. So with very few parameters, you can implement these constructions because all you need to implement is these two functionalities. And with even more properties of attention, which is the self-attention, you can actually implement even shorter solutions for these problems. And I'll just end, since I'm running out of time, to show that in practice, actually, we try to train transformers to solve all these tasks on these semi-automata. And in fact, they do this in very, very low depth. So if here you can see the layers and the accuracy that you're getting. So very fast, you can get like 99% accuracy with very few layers. So they actually train in practice, and they do learn attention patterns very similar to what we showed, where they either do uniform attention or they pick out these sparse coordinates that they should look at. And in fact, these are shortcut solutions in the sense that they don't actually generalize outside of the length that you train them in, whereas a recurrent solution would clearly work even if you increase the length of the sequence. So these actually learn these brittle shortcut solutions. So I'm going to end with just saying that in terms of theory, there are a lot of interesting questions because this computational model of self-attention is not very well understood. It can give you gains that are surprising, that are not understood very well, like these shortcut solutions. And we can understand these self-attention heads better. And in terms of experiments, these synthetic controlled setups of like looking at semi-automata or Boolean functions actually gives a lot of insights into how these architectures have inductive biases, how they learn features and other things. There's a lot of line of work that's starting to focus on looking at these synthetic setups inspired by very theoretical models and studying these architectures. So I'll end with thanking my collaborators and I'll take any questions. Thank you.
We have time for one quick question if there's some, or we can have a longer discussion. Then let's just take a 10-minute break and we can